So I'm going to be presenting from behind here because I have some notes on the presenter view. So this is PULS, Processor Supported Ultra Low Latency Scheduling. So this will be a slightly different talk type from the previous two because this is more implementation focused. And I actually appreciated the last two talks because it helps motivate this implementation and solution a little bit more. But my name is Simon and I'm from Texas A&M. And we work very closely with National Instruments and we use some of the hardware. So when you think of pulse, what do you think about? Usually people would think about human pulse. And this is very important because if you don't have a pulse, that means you're probably dead. And that's not a good thing, you don't want to be dead. And in fact, if you think about it, even an inconsistent pulse can result in death. So this maps very closely to network because for some applications, you also need very consistent traffic. And that was in the previous talk, you want consistent traffic. So some applications for such network performance would be virtual reality. Another kind of application that you would like is this IIoT, so Industrial Internet of Things. You want this to control factories. And the last group, I'm not sure what to call it, so I called it Tactile Internet. And you can think of it as remote control of applications like controlling robots, or you want to perform remote surgery, or even something simple like entertainment where you play an instrument on one side and you can stream that control information to another place so you can basically remotely perform for other people. And all these applications have very different requirements. So VR, you might require more throughput. And then for Industrial Internet of Things, you might not need as much throughput. And for Tactile Internet, all you need is the control information, so it's very little throughput, but you may require low latency. So for VR, you need both very high throughput and relatively high frequency of data coming in. But maybe for IIoT, you may not need as much. And then for Tactile Internet, of course, you want low latency, so you require information coming in very quickly as well. So what happens when you don't have it? Well, for VR, it's maybe not so bad. So what will happen is you switch your head, maybe the picture doesn't move with you, and then you get sick. And so that's not the worst case scenario. For IIoT, the worst case scenario would be even worse, because let's say you get some control information and that information doesn't get through, the factory could become unstable, and what could happen is the factory could explode and cause a lot of loss and even death. And Tactile Internet, also again, it depends on the application. If you're doing an entertainment or performing for other people, the crowd may get restless and they might throw things at you, start booing you, which is not too bad. But if you're doing a rescue operation or you're performing surgery, those can have very dire consequences. And so again, that can result in death. So that's the motivation for some of this work. And in fact, not only the frequency, consistency, throughput has to be coming in at well, how should I say this? So similar to your pulse, this information also has to come in at the right time. So throughput alone is not enough. If you switch things around and you get a lot of data throughput in certain times and none in another time, this can also result in the same consequences. So that was our motivation, and in fact, another strong motivation for this is actually one of our colleagues, Yi-Hong, who many of you know, and he actually developed very nice frameworks to start dealing with some of these problems. Now the issue is, he did all the math, he did an analysis, he performed simulation results, and then he came to the point where he wanted to try to implement it on a real system to see how well it actually works. And we couldn't find a way to do this. And so we had another project going on with National Instruments, and he basically approached me and asked, can we do this on the National Instruments equipment? And that was our first shot, and that's how we came up with this PULS, Processor Supported Ultra Low Latency Scheduling. So what is PULS? As the name would suggest, PULS is processor supported. So instead of trying to put stuff in the hardware, we try to do all these complex scheduling decisions on the host machine, so you can get more flexibility and even implement more complicated protocols. If you've dealt with hardware before, implementing algorithms on hardware is not straightforward. So to decrease this time spent on development, we do a lot of this scheduling and decision making on the host. And then the main thing we wanted to do is, even though we do scheduling on a host, there's some overhead associated with that, but we said we can deal with that overhead and don't worry about it too much if we can still meet certain requirement. And for our purposes, we set the requirement as 1 millisecond. So even though you're doing scheduling on the host, you can still receive the packet, transmit, and receive your acknowledgement in 1 millisecond. And this is especially important as well because some of the real systems, there are features that are impossible to implement on a commercial card. And those things would be like tracking deadlines and packet dropping. But because we do it on a host machine, we can do stuff like that. So, main contribution. This is what we claim to be our main contribution. And we have a test bed for experimentation. If you were present at the reception demo poster session on Monday, we had a system there. And we show that we can schedule real-time packets and non-real-time packets on the same system. And we can do packet-by-packet scheduling in under 1 millisecond. So a lot of this works for the policies that develop. The decision to schedule the next packet depends on whether the previous packet's transmission was successful or not. And we do all this while enforcing deadline, as in the previous talk. You don't want to waste network resources by transmitting packets that have already have their deadline that has passed. And also achieve realistic throughput in a real system. So realistic throughput in our case would be 20 to 30 megabits per second over a 20 megahertz bandwidth. And we can increase the bandwidth if you want more throughput. In addition to that, we want to provide some insights as to some of the problems that you might encounter when you're trying to put some of these scheduling policies on hardware. So what components do you put on hardware? What components do you put on software? What are some of the interfacing overhead considerations that you need to take into account? And also some of the limitations of this approach. But ultimately, our main goal is to bridge the gap between theory and implementation. And we believe that with this platform, we contributed to that goal. So very briefly, let me go over the design of PULS. This is a very high-level idea of what we have. And there's basically a packet generation module that generates packets. And then you put it into multiple queues. We have 4 different queues in this scenario. 2 of them are real-time queues, and 2 of them are non-real-time queues. And 2 clients. So one client has 1 real-time queue, 1 non-real-time queue, and the second client will have 1 real-time queue and 1 non-real-time queue. And then we have the scheduler who takes all this queue information and decides how to schedule the queues. And then you prepare the packet, put certain headers on it, send it to the hardware, and the hardware takes care of the file layer processing and transmission of data. And then you eventually get a response or no response. So with the ACK information and ACK feedback, you can update the status, and then the scheduler will make decision based on that feedback. And just to highlight a little bit about the system, the packet generation, the scheduling, and the status update from the FPGAs, these are all happening concurrently.
Yeah. Does this mean there's like 2 classes of traffic or something?
For each client, yes. And I should emphasize that for this paper, we were focusing on downlink traffic. So 2 clients, they have 2 different flows, and it's downlink flows. So I'll explain a little bit on the packet generation. It's fairly straightforward, but basically we have a frequency where packets arrive. So you can say that every 5 milliseconds we want a certain number of packets to arrive, and this can be a random number of packets or it can be deterministic. For our case, we use random number of packets because deterministic is not as interesting. So you have a random number of packet arrivals every certain number of milliseconds, and then you just generate the packets based on that. We also did another experiment to say that, okay, instead of doing this, let's set the packet arrival rate to be very low, but instead of packets arriving deterministically every point, you say that there's a probability that the packets may arrive, and another 1 minus that probability that packets won't arrive. So this is slightly different from deterministically every 5 milliseconds a certain number of packets will arrive. So it's different arrival processes, and this is generated on the platform itself. We can also use UDP ports from other applications to stream packets if you want to run real-time applications on some of the things you want to test on. And then the next thing I want to talk about is the scheduler. So the scheduler, again, looks complicated, but it's fairly straightforward. You basically decide which scheduling policy you want to use. In our case, we tested 4 different policies, which is LDF, the largest deficit first, and then longest queue first, random round robin, and we have the ability to add new custom policies as well. So regardless of which policy you use, what it does is it will take the element from the queue, based on the queue that's specified by the policy, and then first thing you do is you check whether the deadline has elapsed. If it hasn't elapsed, then you send the element to the FPGA and you lock the scheduler. So you won't have queuing delays on the hardware itself. So what we enforce is basically one packet gets scheduled, you wait for the feedback, and then you schedule the next packet. And of course, if the packet has been, the deadline has elapsed for the packet, then you just drop it and you update the deficits appropriately. And while all this is going on, there's also this constant polling of the FPGA state, and that's done in the following way. So the software side, all you have to do is basically read registers on the FPGA and decide whether to lock or unlock the scheduler. And then on the hardware side, what we do is we get the element, we transmit, and then when we get an ACK, we increment the ACK count. If we don't get an ACK, we increment the timeout count. And based on the count change, we feed back that information to the software side, and then the software can update the states. And of course, the first thing we have to do is, well, how much latency is involved with this hardware-software interfacing? And we wanted to characterize this latency. And what we did was we added a few more things just for this experiment, and then we removed it when we were running the whole experiment. So what we did was we added a timestamp that's from the FPGA before the packets go into the queue. So when you generate the packets, you timestamp based on some value that you get from the FPGA, and then when you transmit and you get the ACK back, you compare the timestamps, and then you get an idea of how much latency is incurred in that. And these are the results. The mean is approximately 200 microseconds. And you can see the variance. It's not too bad. You can get the worst case scenario in 316 microseconds. But ultimately, this doesn't affect our main goal of being able to schedule a packet within 1 millisecond. And we did this round trip experiment and showed that regardless of packet size and even at the lowest modulation rate, you can still get a packet, transmit, get the feedback in 1 millisecond. And here, now that we have an idea of how the hardware-software performs, we can run a lot of experiments. And you see a lot of capacity region results in papers showing that some policy works better than others. Here we tested 4 different policies, and each of these points are real points and real experiments that we run. And what I want to say is the key point here is not that you can see, it's not that one policy behaves better than the others, but for this platform, you can actually run all these policies and see how it performs relative to others. So our goal is not coming up with the best policy. Our goal is to take all the policies that people have already come up with and compare them against each other on a real system. And delivery ratio here basically means that 99% of the packets have to be delivered, and the deadline is 5 milliseconds, so 99% of the packets have to be delivered in 5 milliseconds. And the bottom part is a technical part, but basically we are using uniform distribution. If we say KRT is 11, that means there's a 0 to 11 packets uniformly distributed can arrive every however long you specify. In our case, I think we specified to be 5 milliseconds. So every 5 milliseconds, 0 to 11 packets will arrive. Real-time packets will arrive. And NRT is the same for non-real-time packets. And not just capacity region results, but you can also do it with throughputs. You can compare the throughputs of different policies. You can change the requirements of different clients and different flows, change the deadline, change the delivery ratio, and these are different things that you can do with a platform. And of course, you can also compare the loss ratio between the number of packets that's delivered on time versus the total number of packets of packets that have been transmitted. And what you can see is, of course, the optimal policy performs a lot better than the others, and you can see that largest deficit first policy you get 2% error rate, or less than 2% error rate, whereas other policies get 23, 25, as high as 60% for some of the policies in some scenarios. So this gives us a very good idea on how different policies behave under different scenarios. And so that's basically our approach to the thing. And we have a lot of different results that we can show, but again, I want to emphasize that the key point is not the results, but the things that you can do and what kind of results you can get from the platform. So if you'd like to know what other results you can get from this, feel free to ask after the talk as well. In conclusion, basically, PULS, it provides a very useful test bed for experimentation. You have multiple options of protocols that we have already put, but if those policies are not good enough for you, you want to make your own policies, you can do so, and you can compare against the policies that have already been developed. You don't have to rebuild all the policies again. And this works for heterogeneous traffic, real-time and non-real-time flows. It contains features that are not implemented in commercial NICs, and this would be like packet dropping, tracking deadlines, and some of the features we're thinking about as well would be, can you reorder the queues? That's a little bit more complicated, but we are thinking of such kinds of mechanisms. And you'll use a powerful host machine for scheduling algorithms. The host machine, so if you put a processor on the FPGA, you get about 200 megahertz clock rate. The host machine, you get gigahertz clock rate. So that's it's almost, what, 1,000, I would say 10 to 100 times difference. But when you do that, you have to start dealing with the overheads of interfacing between hardware and software. And that comes to the cons of PULS, which means that, again, the hardware-software interface overhead is significant, which I just mentioned. But another thing to keep in mind is you're using the processor on the host machine to do different things. So the more things you do on the processor, your scheduling performance may suffer as a result of that. And we have some ideas on how you can overcome some of these problems. Like, you want to reduce the interfacing overhead. So instead of scheduling one packet, maybe you can schedule multiple packets and do a block decision making. The downside with that is your decision will be optimal for the first one, but may not be optimal for the second, third, fourth, and so on. And then the other thing you can do is do a look-ahead scheduling, which is what we're working on right now. So instead of sending one packet, waiting for a decision, we send one packet, and while it's being transmitted, the next time we send two packets, and based on whether the first packet gets transmitted successfully or not, you transmit one of the two packets that you preload onto the FPGA. So in this way, you can preempt the decision making by giving the hardware two options. And then the moment the hardware receives the feedback, it gets to transmit immediately without waiting for a decision from the host again. The other thing we can try to do is, if you think about it, which queue to transmit is basically a few bits of information. That's all you need. So instead of waiting for the feedback to come about the act, and then transmit the whole data packet, you transmit the data first, and then based on the scheduler decision, you just tell them which queue to schedule. So that's some of the directions that we can go to overcome this interfacing overhead. But ultimately, I guess the question is it reasonable to have a separate coprocessor? So instead of using just one host machine processor to do everything, maybe you can use another processor just to do the scheduling decisions. And this would be a matter of cost benefit, because is it worth it to put an extra processor right next to your network interface card just to do scheduling decisions? And the answer may be no for sub-6, but when you start moving to millimeter wave and 5G type things where you have 2 gigahertz bandwidth, this latency becomes very important, and you want to make the best decision on scheduling. So maybe in that case, you want to put a scheduler. Right next to the NICs. So these are some of the questions that we're exploring, and yep, that's the end of my talk.